Let's look at how the tool calculates net delay. In this module, we'll look at what wire load models are and how they're used to calculate net delays. We'll also identify the different file formats that are used in the various tools that represent the wire delay information. Your design layout uses different metal layers and vias to connect the various gates or cells in your design, and thus they are called interconnects or wires. The metal layers inherently have a delay because of the resistance and capacitance, i.e. the physical properties of the metal layers themselves. This inherent delay of the metal layers used to connect the cells is also known as interconnect delay, or wire delay, or simply net delay. The net delays are calculated typically from 50% of the input to 50% of the output. It is important to notice is that all these interconnects are naturally positively unate. The timing arcs of the nets connect the timing arcs of the cells to form a timing path. The timing of these timing paths are then verified against any given requirements to make sure your design works. Routing tools like NanoRoute that you see here are what are employed by the physical design tools to lay down the metal layers or the wires. Physical tools use routing and extraction to determine the actual wire delays by laying down the metal layers to connect the various cells in your design. But the front-end synthesis tools like Cadence Genus do not have that luxury. So, they need to rely on some form of wire delay estimation to accurately predict the path delays. Wire delay estimation can be done either through wire load models or a layout wire delay estimation tool like the Physical Layout Estimation or PLE in Cadence Genus synthesis solution. The wire load models or PLE must accurately predict the wire delays to meet the requirements of your design. Therefore, they need to correlate to the actual routing performed by the physical design tools. The foundries supply the wire load models along with the timing libraries, and you can plug the wire load models into your static timing analysis tool to calculate your net delays. Unfortunately, one of the cons of wire load models is that they are statistical, and they're calculated by the foundries based on the nearest enclosing block area. So, based on a given block size, the STA tools must predict what the actual wire length from a cell to another cell must be. This can be error-prone, because not every cell in the design is placed at these estimated wire lengths. Furthermore, we use a guess for the fan-outs and loads to estimate the maximum wire length, then calculate the corresponding resistance and capacitance of the estimated wire length, and finally the delay of the wire. This multi-step process can be very tedious and result in a very pessimistic view of the wire delays and thus the design we want to create. Thus, wire load models can be challenging when it comes to correlation to the actual place and route tools. Nowadays, with tools like PLE and Genus, when you provide the process technology files and the floor plan of your design, they try to calculate wire delays dynamically. The correlation with PLE is much better than the wire load models and is much closer to the routing tools. The wire load models are calculated based on the average statistical net length over many designs. A Poisson distribution such as what's shown here is used to determine the average net length for nets in a certain block. Average statistical net lengths thus determine the corresponding resistance and capacitance, and thus you calculate the delay of that net. These net lengths that are statistically weighted make the wire loads pessimistic and thus might be unreliable for some designs. But, because they provide a good estimate, you could use them as a good starting point for synthesis or even for critical path analysis right after the synthesis stage. In the graph, notice that the larger block sizes and larger fanouts have larger capacitances, and thus larger delays. To reduce pessimism, you may choose to generate custom wire load models based on your design from certain tools, instead of using the generic wire load models provided by your library vendor. To minimize pessimism or to simplify the net delay calculation, you can choose one of the multiple modes that the STA tools might allow, such as the top mode, the enclosed mode, and the segmented mode. Depending on the mode that is being used, varying block sizes are selected for the wire load model selection table. Therefore, to calculate net delay using wire load models method, you need various wire load models based on various block sizes. The STA tool determines an area that a particular net fits into and using the wire load selection table selects the block area that encloses the area of the net. Then, you use the wire load model to obtain the average wire length for a given fanout and block size. You finally use the capacitance multiplier and resistance multiplier to determine the delay of the net. This example shows the wire load selection table. If the block area is between 0 and 203, then the tool selects the B.5.5 B.5.5 wire load model. The actual wire load model looks similar to this, where you have these kinds of resistance multipliers and capacitance multipliers. And the RC is now calculated based on the capacitance of the wire and resistance of the wire. Try this activity to test your understanding of the concepts discussed. Initially, when you start out with your synthesis, you're using the wire load models, but then when you get to your place en route, and it is done, you can now generate the extracted data, which is either in the form of a SPEF or an SDF. This extracted data can be passed back to your synthesis tools, which is called backannotation. You can send this information back to the synthesis to get more accurate timing data for your net delays. Synthesis can now do a better job of optimizing the rest of the design based on the net timing information. Extraction tools can create models for your RC network using some sort of compression or reduction mechanism to generate either 2D models, 3D models, or 2.5D models of your layout. These RC models, when reduced, give you either the RSPF or DSPF or the more commonly used SPEF standard parasitic exchange format. This process is called extraction. The SPEF is mentioned here as the industry-wide standard format. This SPEF is later converted into delays standard delay format, SDF, by the delay calculators. You can take either the SDF to feed back into your synthesis, or the SPEF can be used to feed back into your synthesis. This process is called backannotation. One of the steps of backannotation is delay calculation. If we are feeding the tools, delays of the nets, then we need to have a delay calculator that does that portion of converting your RC network into a delay network. This process is called delay calculation. Usually, statistical analysis requires the net delays be provided either through an SDF or the SPEF, then converted internally through their delay calculators and then used to plug in the net delays when doing an optimization. Either way, these net delays are calculated, and so delay calculation plays an important piece of your whole backannotation process. The accuracy of your net delays depend on both the extraction tools as well as the delay calculation mechanism that is being used. Different formats provide different levels of accuracy and runtimes. Some of the larger file sizes come with longer runtimes, and therefore it may take more time to generate these particular files. When you reduce them and make it simpler, it's faster to read into the tools. The delay calculation is something that is happening in either the front end or the back end. You can start out with DSPF or with the SPEF and then bring that information directly into your synthesis tool and then let the synthesis tool do the delay calculation. Or, you can do the calculation ahead of time and then bring in an SDF. It all depends on what formats are being used. You're trying to justify the runtime with the amount of accuracy that you prefer. So, you generate these kinds of correlation numbers that correlate between your front-end tools and your back-end tools even if you have to sacrifice some accuracy so that you can meet your design goals faster.